I'll compliment in a different way or something.
Right. Just change the wording slightly.
Live stream's up and running, so whenever you want to start. Whenever you want to go.
Okay. We could take adjust.
You are good.
Oh, okay, everybody just quieted down, so I'll go ahead and start. That's maybe the first time in all of the introductions I've ever given that the whole room just went silent at the same time. Okay, yeah, it's my pleasure to introduce, I guess, our first seminar of the spring semester here. This is Cameron Bertossa's PhD defense. So Cameron grew up in, as I understand it, snowy Florida, which, if you're following the weather, there's been some pretty crazy weather down south this week. But came, and I think you said it's record snowfall in where you're from, right?
Yeah, there's been a lot of
Several. It's a lot of snow. But then he moved north and graduated his undergraduate degree from Cornell University before coming here. And then there's kind of an interesting sequence of events that transpired around when he came here. So first of all, when he was at Cornell, he was on the rowing team, and they were preparing for end of season or mid-season competition, I guess, or early season competition, I don't know. But anyway, they had practice, and so Cameron, I didn't realize this, flew out the day of the prospective grad student visit. I did a whirlwind tour of the department, met with a few faculty, myself included, and flew back and actually did practice in Cornell that day. So that was, fairly impressive. Then on top of that, after making the offer, a couple months later, in March 2020, as you all know, we all kind of shut down here for the pandemic. So Cameron then started school remotely. And we did, well, not remotely, I mean, he was in town, but we were working virtually. And the second time I met Cameron was actually March of 2021, a year after he started working for me. But he was extremely productive. In the 4.5 years he's been here, he's already done a significant amount of research, both on the polar radiant energy in the far infrared, the pre-fire mission, working on some algorithms for that. But also what he's going to be talking about today is kind of his passion is trying to understand the different cloud states that occur in the Arctic, how they might be changing, and how they may be feeding back on the Arctic climate. So with that, I'll hand it off to Cameron.
All right, green light's on. Sound good?
Green is good.
Green is good. Okay, yeah, so thanks everyone for coming. I know people might be burned out from AMS week and lots of talks, but here's one more. So I'm going to start with kind of just standard why we care about the poles and why we study them. So one major reason being that poles largely act as kind of this heat sink. So you can see this on this schematic to the left here, or I guess your right, where we've got the surplus of energy that we receive in the tropics, largely due to increased shortwave radiation, versus we've got these deficits out in the poles. And so to kind of rectify this meridional gradient, we'll transfer heat through the form of atmospheric and oceanic processes to kind of fill this. And so you can imagine if we've got changing environmental conditions in the high latitudes, this deficit might change, and therefore that heat transfer process also might change. And so beyond this, though, we know that the poles are areas of rapid change, particularly the Arctic. And so, you can kind of pick your poison in terms of how you want to look at this, but a major one being our sea ice extent. So here's a plot of both March sea ice area and September sea ice area. March being the month where we got kind of a climatological high in sea ice, and September being a climatological minimum. And you can see in both months we've got very clear decreasing trends, but this trend is very clearly enhanced in our minimum month. And that kind of ties to this idea of the high latitudes having a lot of these really strong feedback mechanisms. And so in this particular case, we might think of the ice albedo feedback, where as you've got less ice, your surface becomes less reflective, so you absorb more short-wave radiation. You warm the surface, you melt more ice, and the feedback kind of continues. And so, this was maybe hinted at in the first slide, but long-wave radiation is really important in the high latitudes. And so we can look at this with this diagram on the right, where in red and blue we've got incoming at the surface long-wave radiation in blue, and then short-wave radiation in red. And you can see for most of the year, or all the year, long-wave radiation dominates, but particularly when you start to look into the winter months, when your solar zenith angles are really high, your short-wave term essentially drops to zero. And so, all the incident radiation at the surface is entirely determined by what's going on with your long wave. And so, kind of tied to this, we can think about, okay, what effect do clouds have in the atmosphere and on the surface? And so you'll see that here in gray, red, and blue, where clouds can have a cooling effect in the short wave, where if you've got a cloud, it's a highly reflective surface, reflects more short-wave radiation, or it can have, kind of act as a blanket in your long wave and trap radiation, thermal radiation near the surface. And so they've got these kind of competing effects, and you can see what the net term is in gray. And for much of the year, you'll see that kind of thermal insulation effect dominates, and clouds largely warm the surface in the high latitudes. And so Radiative et al. In 2014 has this really nice study where they kind of show that DLR, down-dwelling long-wave radiation, can be described as this inclusive variable in the Arctic, meaning if you know what's going on with your DLR, you know what's going on with a lot of other kind of important geophysical climate variables, surface temperature, water vapor, etc. And so, given all this, there's been a lot of really interesting findings kind of stemming from this Shiva campaign that took place in the October 1997 through October 1998, where what they did was they had one of these big icebreaker ships that they kind of rammed into the pack ice and let it drift along for the year. And aboard that ship, they had, a whole slew of different instrumentation looking at ocean, atmosphere, surface. I think they were really trying to target, kind of ocean-atmosphere coupling mechanisms in the Arctic. And so what they found was, in this region at least, that the Arctic really tends to sit between these two kind of preferred states, where one's described as transmissive, so a lot of radiation can escape from the surface, and one's described as opaque, so relatively little radiation can escape from the surface. And you can see that here in this time series. In this case, it's just net long-wave radiation at the surface. And if you kind of squint your eyes, you can kind of see you tend to bounce in between these two preferred values. So, for example, here you've got this maybe 10-day stretch where you sit at negative 40 watts per meter squared, so this means a lot of radiation escaping from the surface, and you might be cooling the surface and promoting the formation of ice, and then within a few hours you transition into this relatively opaque state. And if you essentially collapse this time series and make a histogram more or less, you'll see that these two kind of clear modes arise. Okay, and so we see this behavior in not just net long-wave radiation, but also DLR, so the radiation incident on the surface, in various different studies in similar areas, but different years. So kind of this feature of there being two modes is consistent. And so there's kind of this natural question of okay, what's actually leading to this? And so this is really interesting, and this has kind of been largely assumed to be associated with these Arctic mixed-phase clouds, which have received kind of a ton of literature in the past couple decades, but I think they're still a really hot topic right now. And these clouds are really, really challenging. but I think kind of excites a lot of the research. So I've just taken a quick screenshot from Google Scholar. There's a bunch of articles referencing them, and then there's this what I think is a funny schematic from Morrison et al. 2012, where they say they try to simplify the interactions and various processes associated with these clouds. And you can see it's just this kind of hodgepodge of large-scale dynamics, microphysical properties, interactions with the surface, et cetera, all kind of convalescing into one that lead to these extended lifetimes of these clouds. And so, maybe as I should back up and say, as the name implies, these clouds have both supercooled liquid water in them, as well as ice particles. And this supercooled liquid water, in particular, acts as really effective emitters of thermal radiation. And so, the basic idea of how these clouds connect to these states is that, if you've got this mixed phase cloud with these effective, that acts as this effective emitter, you get your insulating effect and you trap a lot of radiation at the surface, and this is kind of your opaque state. Versus, when you lack these mixed phase clouds, your Arctic atmosphere is really dry and doesn't emit very much thermal radiation, and so that's when you're in your transmissive state. And so, this is really interesting, but why is this important and what I'm calling a potential problem? Well, it means that your mean state's not a good kind of physical representation of what's going on in your climate, and I'll kind of walk through what that means and why that's important with a set of these contrived examples that I've made. So let's start with this idea of, oftentimes we'll use, we'll look at how well does, for example, a climate model capture the mean of what we see in observations. And in the case of these, in the presence of, what might be going on in the Arctic, where we have these two preferred states, I'll kind of represent that with this blue curve here. So say this is truth, say this is what, we want our models to be able to capture. If we just look at the mean of distributions and how well those are captured, we can look at these two different models that I've made where, model 1 is in red, model green is in 2. We can see in model 2, it looks pretty close to what we're calling truth, where we've got this evidence of two very clear modes, but maybe those modes are just occurring at slightly the wrong frequency for model 2. If we're only evaluating these models with how well they capture the mean or variance of observations, we would say in this context, okay, model 1's actually outperforming model 2, when I would say that model 2 is very likely actually capturing the physical processes that are going on versus model 1. Okay, but beyond this, it also means that we might have kind of this sudden shift in response to changing conditions. So we know the Arctic climate is changing really rapidly, and say one or both of these modes can only persist under certain environmental conditions, and say those environmental conditions suddenly disappear. Well, that means we might get some sudden response in DLR, and we know DLR projects on a bunch of other geophysical variables. Does that mean, okay, the Arctic climate as a whole is going to have this really sudden shift? Okay, so all interesting questions and things to think about. So kind of as I go through this, I want to highlight a few things that I'm going to be kind of asking myself throughout this research. And so one being, a lot of these findings in previous literature, kind of seeing the existence of these states, are based a lot on the Shiba campaign, which is this relatively local area in the Western Arctic. And we know the Arctic's an incredibly inhomogeneous place. So I've just plotted 4 kind of important geophysical variables I've drawn out of a hat. reanalysis data, and you can see very clearly that, there's a lot of spatial structure to these. And so how likely is it that, what we see is going on here is representative of the wider Arctic? That's a question we're going to be looking at. But also, we know that, non-liquid containing clouds, so ice-only clouds are common in the Arctic as well. And specifically, this study by Shoup in 2011 finds these geometrically thick ice clouds are common, where geometrically thick clouds might contain a lot of ice particles. These should also be good emitters of thermal radiation. I've picked a study where they show the effect they have on meltwater runoff in Greenland. And so there's, again, kind of these natural questions of, do these clouds also play a role in these states? Or is it truly just the existence of these mixed phase clouds? Okay, so here's an outline of kind of what I'll be covering. So I've spoken about these two, but I'm going to start with this question of, are the frequency or the properties of these states changing? Because I think this also helps motivate, whether we should be caring about this or not. Are those kind of synthetic examples that are showing actually what's going on in reality? If so, okay, maybe that means, yeah, this is important. So I'm going to start by exploring this with some just kind of simple NSA data. So this is, I'm going to be using the DOE's ARMS site in the North Slope of Alaska. So that's this red star here. And this is kind of nice because it'll base us a bit in the previous literature concerning the Sheba campaign, where Sheba occurred here, NSA occurred here. It gives us a little bit of basis to work off. But also, Christopher Cox did a few nice studies showing how this NASA site is one representative of kind of the wider Western Arctic. So, it might tell us, okay, these findings from this particular site might be able to be extrapolated to a larger area. But two, he also found that the conditions of this particular site is really strongly affected by your sea ice field. So, you sit right along the coast. We know Arctic sea ice is changing, and so this might give us kind of a tie to that physical mechanism as well. Okay, so some specifics about the data set I'm using. I'll just be looking at this hourly DLR data captured by this radiometer sitting on a stand from this site, and it's a set of quality controlled data. Okay, so I'm going to start by just showing kind of a simple time series from this data set. And at the top here, this is just a 3-month span from kind of a randomly picked year in 2001. So this is the fall, start of September till the end of November. So it's a time series of DLR, and then a corresponding histogram associated with this. And if we zoom in kind of on this final 10 days, so 10 days in November, you can see this kind of preferred behavior is evident really nicely in this 10 days. So we sit at, for maybe 3 or 4 days, this relatively high set of DLR values, and in a matter of 4 or 5 hours, we transition to these relatively low DLR values and sit there for 4 or 5 days and go back and forth. And again, if you make a histogram of this time series, you see these two modes kind of arise, which is nice to see. It might tell us that this data set can be used to look at these states that we were trying to find. Okay, so now let's actually try to look at, are these states changing at all? How's DLR responding, etc. So what I'm showing here is, in the left column, I'm kind of separating just by the standard DJF, MAM, etc. And I'm plotting scatters for those each season, for each year, what's the DLR value, and trend lines associated with all those months. And then in the right column, I'm doing kind of like an epoch difference where I'll take my first 5 years that I have on record, so 1999 through 2003, plot a distribution of DLR, and then I'll compare that to my most recent 5 years on record. And I mean, so there's kind of a lot of different things you can look at here. I guess some of the major things I'll point out is, we see positive trends in DLR in all year seasons. It's non-uniform though, so we see kind of enhanced trends in our transition seasons, so spring and fall. In some of these different 5-year distribution periods, you can see the existence of two modes, and in some places you can't. So if we look at spring, for example, this is kind of a nice case where you see in your historical period, you've got kind of the existence of this large transmissive mode, and maybe indications of a opaque mode, but it's not really present. And then if you look at your more recent period, these two modes are much more clear, and your more opaque mode has grown. And you can look at kind of how is the mean of DLR, which I list in the top of all these panels, responded in each of those different periods. Okay, so that's interesting, but I'm going to just maybe focus on the fall here for this talk, because I think it shows some of the things we were searching for at the start. So these are the exact same plots, just separated for September, October, and November. And on top of it, I'm also plotting the anomalous sea ice extent for each of these months. So, darker shades of red are less ice. And so the main thing I want to point out is that you see in November, we've got this really enhanced trend relative to some of your other months. And maybe this is semi-connected to your sea ice field. You can see you've got lots of kind of bluer shades when you've got lower DLR, and you've got more red shades than your higher DLR years. And if we look at our two distributions, we can see that this evidence of these two modes and how those modes have shifted is really clear in this case. So again, we've got in our kind of historical period this clear evidence of these two modes versus in our more recent period, that transmissive mode has kind of entirely disappeared, and we're almost entirely existing in this opaque state. And again, if we look at how our mean has responded, we're 30 plus watts per meter squared difference, which is a really large forcing on the surface. Okay, so I'm going to skip this slide and just kind of cut to say that we find that this enhanced sensitivity in November can really clearly be connected to kind of this addition of effects of we've got increased long-range transport of water vapor, but also you've got these local enhancements caused by less CX. And this agrees really well with some previous studies. Ariel Morrison had a really nice set of studies in 2018 and 2019, kind of looking at how your cloud fields and how your surface gets coupled to your atmosphere, especially strong in the fall versus kind of in your warmer months, caused by your ocean is really warm, your atmosphere is cooling down really rapidly, and so your coupling is really strong because you've got a really strong gradient at the surface. And so, right, and then also, I've taken this quote from Asya Ruff, who, again, also was at one point doing some stuff with Jin K, where, she says, future November may start to look more like present October, and you know, we can look at this data and see that this kind of claim is already being exhibited in some of these observations. And so in particular, I'll show kind of our historical period in October from DLR, in this DLR space, and then our kind of historical period of November and our present day period of November. And what you should be seeing is that, you know, our present day November distribution, so this black solid line, much more closely looks much closer to past October than it does to its past November. And so again, this kind of might align with what Asya is saying, where our Novembers are starting to approach the behavior of October. Okay, so this is really exciting, and you know, kind of what we were hoping to see. Well, hoping is the wrong wordage. It's not good for civilization. Good for research funding. Yeah, we see kind of this what looks to be this collapse of this mode and this really large response in DLR. And so this still kind of begs the question of, you know, is this behavior evident elsewhere, and is it kind of representative of the wider Arctic and you know, also the Antarctic? It's also a cold and dry place. Do we see the same behavior? And so this is a really difficult question to answer with you know, observations similar to what I just showed, just because, you know, that 25 years of data like that is relatively sparse in the Arctic. And so we're going to try to look at this with using CloudSat Calypso data. So the goal is to see if we can use these, you know, polar orbiting satellites to kind of explore this behavior in a more systematic, kind of widespread way. And what's nice about these is you know, we know they're really good at capturing these mixed phase clouds, and we know or expect that mixed phase clouds are going to have a large role in the presence of these states. And so we can see that here with kind of this figure at the left or on the right, where you know, on this top panel here, we see that the Calypso LiDAR attenuates really strongly with your supercooled liquid water layer, whereas your CPR can penetrate that layer and capture maybe some of the ice structure underneath. Okay, so I'm going to again start by just kind of showing an example swath of some of this data. So I'll take a kind of random overpass from this data set where, you know, this particular swath segment is kind of in your North Atlantic storm track region, starting at this green diamond and ending, the swath will end at this red diamond. And so this large panel in the middle is what your CPR, so your CloudSat radar sees, its reflectivity. And then at the bottom, this is some cloud phase information given by kind of the joint products, as well as what your DLR is modeled to be. And so, you know, maybe you can already see in this bottom structure, we can make a histogram of these values and see what our DLR looks like just for this particular swath. And again, this kind of presence of two modes arises. And so, okay, you know, maybe already a promising sign. But you know, there's kind of a natural question of, you know, given we're looking at surface radiation, how well does this kind of top-down view of the atmosphere, you know, how well can these instruments capture these surface fluxes? And so what I'll do is kind of just a simple comparison study where I'll make like a 1 degree by 1 degree box around our NSA station that we just looked at. And anytime a CloudSat or Calypso overpass intersects that 1 degree by 1 degree box, I'm going to match up the radiative fluxes. And so that's what you see here on the right, on the right. And the main thing being that these two distributions look relatively similar to one another, and so we'll say that this instrument or these pair of instruments do well in capturing kind of these exhibited or the distribution of surface fluxes. And this is not kind of a unique finding. This is supported by a lot of these other different studies. Okay, but before we dive in and start looking, we need to be a little careful. And this goes back to one of our first slides. We don't expect the Arctic to behave homogeneously, so we don't want to just kind of group it all as one and look at all these, treat it as one big thing and look at what does clouds eclipse say across. So what I'm going to do just to help guide some of this discussion is I'm actually going to separate the Arctic into these subregions. And I'll do that with just a really simple clustering process where I'll kind of just grid the data across the Arctic and generate distributions for that gridded data, and I'll say, okay, grid boxes with similar distributions, make those one region. Grid boxes with different distributions should be a separate region. And we can see what that looks like here, where for each column, it's showing a different number of clusters to be made. And so each of your unique colors is a unique subregion, and on the bottom panel, you'll see what the corresponding distribution looks like. And so, maybe not surprising, your North Atlantic region is really warm and moist relative to the rest of your Arctic. And so that's kind of the first unique subregion, and you can see it corresponds to these relatively large DLR values compared to the remainder of the Arctic. Adding additional cluster, you get your Greenland region kind of separates out. It has almost the opposite behavior where it's relatively dry and cold, and so your DLR values are much lower. And as you increase your number of clusters, these differences get to be kind of a little bit more minute. And so I'm going to settle on using 3 clusters here to kind of guide this discussion. Might need to use more for your particular case, but in this case it ends up being sufficient. Okay, so now I'm going to just take a few really good examples where we see this signal of bimodality kind of arise from these different clusters, and I'll show different seasons here, and I've tried to color these boxes corresponding to those regions, and so I'll walk through what these plots exactly are showing, but basically your kind of total PDF is this gray dash line, and then I'm separating that by cases in which you identify a cloud in your dotted lines, and then cases in which you identify a cloud in your solid line, and cases where it's a clear sky scene in your dotted line. And so, maybe not super surprising, you can see really clearly that these modes are in some way connected to there being either clouds in the scene or there being clouds not in the scene. And so, we can look at this particular case of Greenland during JJA and see that, our most extreme low values in DLR are associated with cold and dry scenes. Our highest DLR values might be associated with really thick and warm clouds. And then there's kind of, some skew in between of really warm and moist but cloud-free scenes, and really cold and thin cloudy scenes. And those kind of separate distributions overlap on one another. And so I'm going to show essentially these plots, but in a slightly different way, to kind of explore what's going on here a bit more explicitly. And so, this is the plot we just looked at. I'm going to translate it into this, where our blue curve here is simply our total PDF, so the dashed gray line. And then what we can do is we can kind of do this hypothetical of ripping out all the clouds in these scenes, and that's what is this orange line. So this is what's left with just clear sky emission, so if there were no clouds in our atmosphere. And then, kind of paired with that, we can see what is the radiative effect of those clouds. And so that's, called your cloud radiative effect. And that's this red dash curve. And what should pop out is that this cloud radiative effect specifically has kind of this presence of a really specific opaque mode, and then also this smaller transmissive mode, versus your clear sky orange curve is somewhat unimodal. Okay, and so, you can kind of then look at this massive matrix of, your 3 different regions for your 4 different seasons, and see a bunch of structure. But the main thing to point out is that kind of structure in your cloud radiative effect mode. So this opaque mode is present almost in all these panels, modified to varying degrees based on your location and season. And so I think understanding why you get these 2 modes in your DLR distribution, and so your blue curve, can be really nicely kind of shown with this Goldilocks scenario, where in the case of your baby bear, your opaque cloud mode is too small. So this is what I'm calling too few, so you don't have enough of these opaque clouds. And so what happens is this opaque mode isn't very large, and so your total distribution looks mostly like your clear sky distribution. And then in the case of your papa bear, you can see this in our North Atlantic region during spring. This is your 2 mini case, where we're almost entirely always sitting in the presence of these really opaque clouds. So what that does is you essentially take your clear sky distribution and you just shift it over by the magnitude of this mode. So you shift it over by roughly 75 watts per meter squared. And then your mama bear is just right. And so in this case, you've got this nice balance of occurrence of these opaque clouds, as well as a large occurrence of cloud-free or relatively transmissive clouds. And then that leads to this nice balance of the clear presence of these 2 modes. Okay, and then I'll just say, and flash this on the screen, that in the Antarctic, we see very similar behavior, where we'll also separate it with this kind of these 3 different clusters, and if you just kind of look at kind of your continental boundary region, you see the presence of these bimodal distributions, also very common. And so we can use very similar distributions looking at this cloud radiative effect to answer one of our questions, where we'll look at our cloud radiative effect distributions, but we'll break it down by ice clouds, liquid only clouds, and then these mixed phase clouds, and look at what portion of those comprise our total PDF. And you'll see in a lot of these places, so your ice only clouds in blue have this similar modal structure, where you've got some recurrence of transmissive clouds, and then you've got this hump around your opaque mode. And so that's really interesting because it says that to get these bimodal distributions, you're not explicitly required to have these liquid containing clouds. Okay, and so this still leaves the question of, well, why does the two modes in cloud wave effect occur? And we can trace this back to a really simple mechanism of our cloud wave effect saturates really rapidly in the long wave. So what that means is if we kind of just plot distributions of cloud wave effect as a function of water path, so we're putting more stuff in the clouds further to the right here, we see these curves as they have this asymptotic behavior where they'll saturate at a value of 80 watts per meter squared or whatever in this kind of synthetic case. And you can imagine if we were to kind of just take one of these curves, well, actually I should go back and say that while our ice cloud in blue here versus our liquid cloud in red, our ice cloud saturates slower, it still saturates in a similar way. And so you can pick, one of these curves, and you can imagine if we were to just randomly sample from this line, a lot of your values, or a lot of those samples would have a similar value. And that's essentially representing what's leading to this opaque mode. And then, this transmissive mode might be partly cloud-free scenes, and it might be partly some of these relatively low water path clouds. And we can see this, beyond kind of these schematics that I've shown, we can see this in observations where I'm going to look at a similar thing, but I'm going to look at these kind of 2D histograms now, where on the x we've got liquid water path, so this is just looking at liquid clouds, so liquid water path on the x-axis, and then cloud base height on the y-axis. And so you might think of this synonymous as like the emission temperature of your cloud. And then on top I'm plotting the relative frequency of these clouds in this various bins, and then the mean associated with, the mean radiative effect associated with these bins is the colors. And so what you can see is, we've got a lot of red here, so that's kind of associated with these values of 50, 60, 70 plus watts per meter squared aligning with our opaque mode. And we've got a lot of liquid clouds kind of sitting in these values, and this aligns with these orange and green curves. So almost all our liquid clouds are contributing to the opaque mode. We have very few clouds that sit in like this transmissive space, and so in this space here. And again, we don't see a lot of transmissive liquid containing clouds, which aligns again a lot with previous studies. Versus if we do the same thing but look at our ice clouds, similar-ish behavior, a lot of kind of stuff sitting in this red space. Again, that should be associated with what we're seeing here, maybe. Maybe a bit more bleed out, which we kind of see with these distributions. But then we've got this kind of second bullseye up here in the top left, where we've got a lot of ice clouds that are relatively high in altitude, relatively low in water path. So maybe these are like your within Cirrus or whatever, and so that aligns with kind of this portion of the blue curve where these don't have a large radiative effect on the surface. Okay, and so I'll kind of end or get towards the end here with some motivation of we know kind of the wider Arctic is having this declining sea ice behavior, and we've seen, at least with our NSA data, that this signal of this transmissive mode disappearing and this enhanced DLR response can somewhat be strongly linked to this changing sea ice field. We see kind of similar association in our wider data collected by Clouds at Calypso. So I'm going to show similar plots as before, different seasons, but I'm going to just look at ocean-covered scenes versus sea ice-covered scenes. And the thing I want to point out here is that in all your comparisons here, so compare vertically, so in all our sea ice-covered scenes, the frequency of these opaque cloud modes, these opaque clouds is less than that in our ocean-covered scenes. So, it's not uniform across the board, but it's always larger. And so, that might allow me to infer that, okay, this kind of similar signal that we saw in the NSA data might be occurring in the wider Arctic. Okay, and so I'm at 316, so I'm going to just flash my conclusions here and say, answers to these questions are the frequency or properties of these states changing. NSA site indicates that yes, maybe some also affirmations from our Clouds at Calypso data. Do these exist across the Arctic and Antarctic? Seems like it. Are liquid-containing clouds required? Not necessarily. Definitely large enhancers of these states, one of the main components, but not explicitly required. Gonna skip future work. Happy to talk about this more. Gotta go to acknowledgements. Okay, so I need to acknowledge my advisor, Tristan. He always gave me a lot of freedom in exploring stuff, which didn't know what I wanted to do for a while, still don't know what I wanted to do. So it was really nice for him to just let me screw around for a while and do stuff that I enjoyed. I think that's what I've enjoyed about grad school the most, is just being able to do stuff that I like. I've listed a bunch of people here. I couldn't list more names, so I had to include more photos of pets. I've got people listed here thanking friends and family and pets. I have friends and family. These are only photos of pets, but they're so cute. So yeah, thank you everyone. Thanks to my parents for coming out. They came out from Montana, helping me do house stuff. Rory and I, my wife, just bought our first house. Thank you, Rory, for supporting me emotionally and financially through this very long process. Thanks to my pets, I haven't mentioned them yet, for being cute. Okay, and that's all I have.
All right, we have some questions for Cameron, and again, we'll start with students, if there's some questions from students in the audience. I guess, Cam, you can just call on people.
Sure.
Ian.
Do you have a sense of how long each state lasts, and then how has kind of evolved through your NSA data set?
I don't know how it's evolved. That's a really awesome suggestion, and something I've thought about would be, I think the NSA data set's going to be a really good way to explore that. I think it's, in terms of like what we've seen, I think it's really variable. So I've seen stuff with like the mixed phase clouds in particular persisting for 10 to 14 days, which seems very long to me. But I do think it's really variable, and I think it's because they're kind of a fickle beast with, you've got, maybe they're persisting locally for a while through coupling to the surface, and then maybe you've got a storm that rolls through and just blows everything up and they die. And it seems like several days at least is typical, but I think it's really variable.
Is this bimodal phase unique to the polar regions, or does it happen elsewhere in the world? I'm just curious if it's the deserts experience is kind of DLR.
There's not a sharp, it's not like there's a sharp cutoff, when you go below 60 degrees, but what I've looked at is it is definitely unique to, it's enhanced in the high latitudes. And so and you can imagine this, if we do the opposite extreme of looking at in the tropics. you've got a lot of water vapor in your atmosphere, especially near the surface. And so if you look at like distributions of cloud radiative effect, the long wave cloud radiative effect, you don't get that opaque mode because your atmosphere is always sitting in this really incredibly emissive state. It can't really enhance, or they don't enhance your emission as large an amount, right at the surface at least. But yeah. Right.
You showed a really nice comparison between the trips of clouds that PR and the DOE measurements. But kind of at the beginning, were suggesting they may not be representative because of the heterogeneity. Have you looked at the trends that you get from trips of clouds that in your different clusters and see if they're different, or is there not long enough to go up?
Yeah, so like a lot of the CloudSat Calypso data I used, it was just the 4 years where it's fully functional. I've thought about going back and doing similar stuff with the extended daytime only record. But so what? That's 12 years or 13 years. Yeah, I don't know if it's quite long enough to. It's worth exploring for sure. I don't know how that will shake out. I don't expect it to be I don't expect it to exactly match the NSA site. But it's a great suggestion. Yeah. Oh, actually, I do want to mention one more thing though. But that does motivate another funding project where with EarthCare. So. This is something I mentioned at the end of my dissertation where, EarthCare is now getting launched. I think in the next 2 or 3 years, we should have a pretty good set of data from that. I think it'd be, that's 25 years of separation. I think that'd be an awesome study. Do the exact same thing that I've just done, but, with 25 years later of EarthCare data. I think there's some figuring out in terms of like how you get that to match exactly the sensitivity of CloudSat Calypso and dumbing down the data or whatever. But I expect a lot of people are going to be working on that problem to do for their various projects. But yeah, John.
Yeah, Cameron, I was really intrigued by the too few, too many, and just right example. Do those correspond to separate circulation anomaly distributions on the large scale? Because you did mention something about large scale dynamics, and I never saw much about that in your talk.
Right.
But it might be in your thesis, which I hadn't read. But is there any relationship between those states, those different states, and large scale circulation anomaly states?
I think definitely, yeah. I mean, I haven't done a bunch of like explicit analysis, but like, so like that Radiative. So I guess more generally, there's kind of been the suggested that in your Beaufort Sea region, you have this kind of persistent high pressure anomaly. How associated with, clear sky is if you're sitting in a high pressure state, transition to opaque state when you've got periplanic disturbance, low pressure. And there is a correlation, but you're not strictly required to have that. So like lots of times, you'll see if you look at a time series, you can go from actually a low pressure clear sky state and transition to a clear state that's low pressure. Did I say that correctly? Yeah. It's opposite of what you would intuitively think.
Okay.
And so it's not strictly required by your kind of large scale circulation, but I would be very surprised, or I will say, it's definitely your large scale circulation promotes one way versus the other kind of
Okay, at the transitions. Because
right.
Yeah, sometimes people composite just the standing state and they don't composite the transitions. It might be more interesting to do transitions in this case.
Yeah.
Yeah, that's interesting. Okay, thanks.
Dave.
Yeah, part of the motivation you showed that from the late 90s, early 2000s, you saw one distribution of clouds as transitioning towards more October, like the scenario you showed, was a 4-year comparison to a 4-year comparison. You also mentioned that CloudSat was only showed this, maybe that's not enough to interpret that. Do you think the shift that you're seeing in the Arctic is that significant over? Do you see that transition throughout time? Or is there a specific maybe period of time that we still need to say that maybe this is not just due to internal variability or interannual variability that's driving these shifts? Like how much data or timeline do you think
Right.
you can say like this is solidly
Yeah, I mean, I admittedly haven't done any like time to emergence kind of studies. I'd probably refer to like Hamish or Jonah Shah or use my colleagues as a crutch for that. But I'd be pretty surprised if 25 years wasn't enough to say something about the significance. But I mean, something I need to look into more for sure.
So, continuing with the question of getting a longer time series,
Sure.
I think you've made a pretty good argument here that if you know that there's clouds, and if, I guess as a second thing, if you know what type of cloud it is, you could get a lot of the rest of this information.
Right.
Could you use observational data that's less like high
DLR specific
it's
kind of stuff.
like
Yeah.
just some sort of, but has a much longer time series and say, okay,
Right.
we're using this as a proxy, can we see this sort of thing happening?
Right, yeah, I mean, it's definitely a good suggestion. It's like a difficult, though, thing. It's also hard, though, because it's like, I'm trying to think of active sensors that are long-running, because, you know, a big thing as well is, you know, these mixed-phase clouds are relatively close to the surface, you know, clouds in the Arctic are generally hard to detect with passive sensors, because cold kind of thing, and so it's like you need a right combination of all these different things, and then on top of that, you need it to be longer than X amount of time. So, difficult question, but good thing to look into for sure.
I have a question, just clarification. When you calculated the clustering of the air, did you calculate it for each season, or did you calculate it for a full?
I just threw all the seasons together. It's a year long, and then and then just histogram for the year of DLR data and cluster on that. And I've tried seasons, and it's, you know, using it just for seasons, and it more or less shakes out to be the same. There's small differences, but Greenland ice sheet and then North Atlantic storm tracks have pretty strong forcing to make those pop out.
All right, if there's no other questions, then let's thank Cameron again. And for the committee members, we'll take maybe a 5-minute break and then reconvene here to ask any other questions you may have.